Hello, everyone. Welcome to the side stage. In this block, before next break, we would have 2 lightning talks for 15 minutes each, and then one 30 minutes talk. The first one would be Roshan Raghupati from Marlin protocol. Please welcome.
Hello. Perfect. All right, let's just jump right in. So I'm here to talk about verifiable technologies, their benefits, their problems, and all of that. But more importantly, I'm not really here for this. I'm here more for this. So I'm here to pit all of your favorite verifiable technologies against mine, and let's see who comes out on top. And so here are our challenges for tonight. First up, we have zero knowledge proofs, or like ZK for short. Right? Everybody's favorite, I'm sure. So the claim to fame for zero knowledge proofs is being able to give you a proof of execution for like any piece of compute that you might want to do, right? So it provides cryptographic security, which means that the security of your protocol is just dependent on cold hard mathematics, right? And it's usually single party, which means that you can just take some piece of compute, generate a ZK proof all by yourself without really having to depend on like an external party. And it's also non-interactive, which means that you get to do it without interacting with the outside world at all, even during verification, right? Its main weakness, of course, it's that it's like really slow and expensive. It's usually like orders of magnitude more expensive than just doing the compute by yourself, right? And the kind of subtle problem it also has is the inability to sort of handle shared private state, right? What I mean by this is, in order to generate a ZK proof, even if you have private inputs, the person who's actually generating the ZK proof still needs to know all of the inputs that go into it, right? And if the person who's generating it knows what inputs goes into it, at that point your inputs are like no longer private, right? So yeah, that's ZK. All in all, a pretty formidable challenger here. Let's look at our next one, which is the rookie, FHE, or like fully homomorphic encryption, new kid on the block. It provides cryptographic privacy, which is a little different from cryptographic security, but we'll get into that. It's also single party and non-interactive like ZK, where you can sort of just do the compute on your own without really having to, like relying on like third parties. Like ZK, it's also really slow and expensive, and it also can't really handle shared private state, which is a bit interesting because the whole point of FHE is to handle private computation, right? What I mean here is fundamentally FHE kind of relies on all your inputs and state being encrypted with the same key in order to do compute, right? So let's say if you and I have to do a compute, let's say something like a smart contract, that creates like an obvious conflict where you and I have different keys. That begs the question of whose key is the smart contract state actually encrypted with, right? So something that's a little ironic also about FHE is that it doesn't really provide a correctness proof, right? I mean, we are at Verifiable Summit, but ironically, FHE on its own isn't really verifiable at all, right? You kind of have to combine it with something else to get the verifiability back. Our third challenger, something that I like to call the old guard, is MPC. The claim to fame for MPC is letting you aggregate multiple pieces of computation that are being done by different people into like a single aggregation. That's as though the single person did it by themselves, right? So it provides what I would say is partial cryptographic security, which I'll get into in a bit. But the main claim to fame is that it lets you have shared private state, right? So this is usually some state that you just break it up into pieces, give one piece to each of the guys in the MPC network, and you can sort of now do computation over the shared private state, right? The problem, of course, is that it's slow. I'm starting to see a theme here. It's usually also interactive, which means that the parties that are in your MPC network need to be online and usually interact with each other in order to actually do the MPC, right? And given that, you actually need to have multiple parties in the first place to do it. There are concerns around like collusion of the parties and how they can sort of like break your MPC protocol, right? And the reason why I say partial cryptographic security is because MPC is not usually auditable, in the sense that when you do MPC, the verifiability of your MPC is usually restricted to participants in the MPC. So let's say I'm a participant. I get to verify and check that the persons before me or each other person is sort of doing the work as they should be. But it's not really easy for like an external observer to actually say, the MPC protocol went fine or not, right? And with that, we have the last challenger, the heel, which is TEs. TEs are essentially hardware-isolated environments, which let you prove what sort of code is running inside through a process called remote attestation, right? The only reason why TEs are even in this fight is because TEs are just fast, like blazing fast compared to everything that came before it, right? Forget about orders of magnitude more overhead in all of them. TEs basically give you like a single digit or like low double-digit percentage of overheads. So TEs are also, of course, single party. You just run a TE yourself, generate a remote attestation, generate a proof of that, and you don't need to involve anybody else. They also excel in providing shared private state because given a TE, you and I can basically set up secure channels with the TE, sort of send our private data into it, do some compute on it, and just get the result out, right? And of course, it's non-interactive in case of verification, where I can run some compute in a TE, generate a proof, and like I don't need to be online for other people to sort of like verify that later, right? So I said TEs are single party, but that's only kind of true. At the end of the day, you always have a trusted third party in the case of TEs, which is the hardware manufacturer, right? You're sort of relying on them to manufacture the hardware properly and sort of ensure that the remote attestation process actually works as expected, right? And of course, all the rage today is side channel concerns. TEs are vulnerable to things called like side channels, where you can sort of like compromise the privacy of TEs and like extract keys and do all of that, right? So, okay, here are our 4 challengers. Let's maybe just do a quick poll to see like how many people are actually working in each of these. So, hands up if you guys are working on ZK. And like, feel free to raise your hands for like multiple if you're working on multiple. So, quick poll for ZK. That's quite a bit. What about FHE? And MPC? Great. And TEs? Okay, that's quite a bit. And feel free to let me know after the talk if I got anything wrong. So, okay. Let's take a step back and ask the question of why, right? Like, why pit each of these technologies like against each other? Like, what are you really hoping to get out of it, right? So let's leave that aside for a bit and let's put on our friendship hats and maybe do an epic handshake for like 5 minutes. Yeah? So I want to present to you like what I think are really good use cases for like combinations of these technologies. Let's shed all the fighting hat and let's put on some friendship hats for now. Let's start with the combination of like ZK and MPC, right? One of the oldest combinations of like these 2 technologies was the powers of tau ceremony, and the most recently we also had like a KCG ceremony. The main use case that they solve is that a lot of ZK systems basically require what's called as a trusted setup, right? And this setup process basically involves the combination of randomness from different people, and it basically produces what's called as toxic waste that, if it's leaked, will basically compromise the entire ZK system itself, right? So what powers of tau did was basically use MPC to make it a multi-party. So all the randomness that you need basically comes from multiple people, and all of the toxic waste disposal also is now distributed between multiple people, right? So what this gives you is, even if like one participant is honest enough in the powers of tau ceremony, that basically ensures that your entire ZK system is secure, right? And that basically means that you as a participant could have been in the powers of tau ceremony, could have done your work properly, and that gives you the assurance that the ZK system is like fundamentally secure, right? Let's look at another one, which is the combination of like TE and MPC, which is LIT protocol. LIT's claim to fame is what they call like distributed non-custodial key management. Effectively, what it's giving you is something like account abstraction, where you sort of have like an external owned address for you that's sort of distributed across the network using MPC, right? And you get to define what sort of access control you sort of want around the key. So you might say, hey, okay, maybe if this person has some sort of NFT, maybe give them access to the key or something like that, right? So The main advantage that you get here is that, for one, the MPC network means that your key is distributed, which means you protect against like any single party getting hacked and sort of your key getting leaked, right? And what Ts also give you is sort of like mitigation around like collusion of your MPC parties, right? So because let's say your MPC parties do want to collude, now they also need to do a compromise of, let's say, n different TEs and actually then do the collusion, right? One more. Let's try FHE and MPC. The key example here is Zama, and like Phoenix was using Zama. Their claim to fame is basically providing FHE-based smart contracts. So if you recall, FHE by itself cannot have shared private state because of the problem of like having to have a shared key for basically doing the compute, right? The main innovation here is basically take the shared key, put it across the network, right, using MPC, and boom, you just basically have Zama over there, right? They kind of also use ZK, but I mean, it's not really relevant for this. Next, how about ZK and Ts? We have like examples of Tycho and Scroll. The main use case is something called as a multi-proof. That basically lets you mitigate sort of 0 days in each system. So let's say your ZK system has some sort of like cryptographic vulnerability. I mean, ZK is fairly new, right? Or maybe even your T has vulnerability because of like side channels and stuff like that. What an attacker needs to do here is basically compromise both of these systems in order to execute a successful attack on your network, right? And you can easily extend that to different ZK flavors, different ZK system, maybe a Plonk and a Groth together, or stuff like that, and like even different TE flavors together to sort of like distribute that across like hardware manufacturers, right? Another one, a bit of a plug, which is the stuff that we are building. It's Calypso. So it's basically a proof market that supports confidential inputs, right? And the reason we started building this out was to solve that exact problem, which is the outsourcing of like client-side proof generation. We had a lot of like wallet apps come to us and say, hey, proofs are taking way too long on like mobile devices, on like our consumer devices and all that. So yeah, we kind of built this for that. Essentially what it is you have a whole bunch of ZK provers who are running in Ts, right? And the inputs that go into the ZK proof basically only exist in like plain text inside these Ts. So what that lets you do is you basically get to outsource like client-side proof generation from your mobile devices and stuff like that without really compromising the privacy of these keys, right? So given that have a dedicated network instead of like mobile devices, it's also like a lot more performant, way cheaper, and like more efficient. And especially on mobiles, you also have the concern of like battery, right? You don't want your apps just chewing through a user's battery, and that's like a one-way road to getting dumped by the user. So something else that I didn't really find a lot of examples outside of like research papers and stuff was a combination of like ZK and MPC. The main goal is to basically make MPC auditable for like external observers. So instead of just participants in the MPC being able to prove it, have like a whole ZK proof of the entire MPC computation that happened, and you can sort of like go back and audit that at any time, right? Another thing, maybe let's combine 3 instead of 2. Let's put FHE, MPC, and ZK together. That basically gives us verifiable FHE, right? So the main problem with like FHE and this is that it lacks a correctness proof, right? And you basically just get that through ZK, right? And you can sort of build something similar to Aztec, like a confidential rollup, where your smart contracts basically execute FHE, and you sort of create a ZK proof of that and put it on ETH and sort of like roll it up, right? Let's maybe supercharge this. Let's replace ZK with T. So it kind of solves a whole bunch of problems with like each of these technologies. So FHE basically lacks correctness proofs. Your MPC is like susceptible to some sort of like collusion, right? And of course, your T is susceptible to side channels and like leaking data, right? So T's get you the correctness proof side of things. It also prevents the collusion that is a problem with MPC, right? And what FHE gives you is, even if your TE gets attacked and sort of leaks data, right? Your FHE ensures that the leaked data is still in like an encrypted form, right? And of course, MPC enables the confidential shared state part, which I guess you can sort of get with TE as well, right? And that kind of brings me to the end. This is kind of what I want you to take away, which is at the end of the day, verifiable technologies are tools, right? And like no tool is basically perfect for like everything that you want to do. So pick your use case, pick what tool actually works best for you, right? And don't be afraid to sort of combine tools to take advantage of each other's strengths, and especially to mitigate each other's weaknesses, right? And yeah, that's it from me. I would love to hear if you guys are actually working on combinations of these that I haven't listed over here. Any new exciting combinations would be happy to hear. And yeah, feel free to hit me up after the talk. Thank you.
Maybe some questions? OK.
Hi, thanks a lot for the talk. Like, very interesting. My question sits around, you've explained all the advantage and disadvantage of combining those. Computationally speaking, like, do you have a ranking of all the combinations, basically?
Right. OK. Well, anything that sort of combines T with other stuff is obviously faster because T's themselves are faster, right? And any sort of combinations that MPC is OK if you combine it with other stuff. The main problem is basically doing some sort of like ZK and FHE together, because both of them today are way too slow on their own. And if you combine them together, I don't really know if it's even feasible today.
Like, how do you solve inference problem? Like, how do you solve latency problems when you use FHE with something else, basically?
Latency problems are solved. For example, something like FHE and MPC, right? That's kind of solvable today because both of these things sort of work in different stages of the pipeline. So your MPC just holds the network key, right? So your MPC doesn't really interfere with the execution of FHE. So in that sense, they are sort of orthogonal in terms of performance. Your validators in, like, for example, something like Zama are basically just doing FHE straight up. So.
Thank you.
OK, any other questions? I don't see on this side. OK, thank you, Rohan.
Perfect. Thank you, guys.